All right, everybody, welcome to Notes 2, Radioactive Decay and Nuclear Equations. So today I'm going to kind of be bouncing between several different things. We have our slides right here. In the slides, I have little sections of the notes that you guys will be writing. At the end of these slides, I have the link to the notes, so you can compare the notes that I made versus the notes that you made. And then we will also be completing the packet that you guys hopefully glued in. The first page of that says the nucleus radioactivity on it. So we will be doing all of those problems, all 3 pages together, so that you guys really understand this process before you get the pages to do your actual homework. So what we are chatting about today, right, is radioactive decay. So we started our entire conversation last week with notes on nuclear equations, right? And we talked about 2 things right out of the gate, fusion and fission. So we agreed that fusion was the merging of atoms, right, which releases a bunch of energy, versus fission is when the nucleus of an atom splits, and that also releases an enormous amount of energy. Yesterday, this is me going back and forth, yesterday you guys should have completed this simulation, the PhET simulation. And when you were building your atom, for example, I'm going to build a lithium really quickly. So I just added 3 protons, right? Which is my identity piece. That means I now have lithium. Once I have lithium, I'm going to add some neutrons. And neutrons, of course, are what make our different isotopes. So down here at the bottom right of the screen, I'm going to check nuclear stability. See how lithium is now shaking? That means that it is unstable in this current situation, this current isotope. So I just added another neutron. Now I have 3 protons and 3 neutrons, and it's happy. Let's add another neutron. Still happy. Now it's unhappy again. So today what we're going to talk about is what happens when these atoms become unstable and how they get back to stability. So going back to our slides, let's keep going. So first one, and again, you guys are not going to, I'm going to go to the next slide for a second. When you see slides like this that look just like the notes that I usually give you on the board, this is when you'll pause the video and write out everything that I have. But we're going to start with a little context, and then you guys will go to the next slide, pause, write it all out, and keep going. So radioactive decay is exactly what I was just telling you. It's when an atom is in an isotope that it's not stable in, so it's really unhappy, and therefore it wants to break down or decay until it is more stable and more happy. Imbalance in the number of protons and neutrons is what causes instability. When there's too much energy inside the nucleus, right? Because our protons and our neutrons all have energy associated with them. So if there's too many neutrons in there, there's too much energy. And that's what causes the atom to kind of spaz out and want to get rid of all of the extras. All right, so this will be the introduction for your notes. So go ahead and pause me if you need to, and go ahead and write all of these notes. I'm going to read it out for you as well. So our essential question, how do atoms achieve stability? And our first section is on radioactive decay, which is exactly what I said. It's the breakdown of an unstable nucleus into more stable nuclei, and we're emitting radiation, which is energy. So we're getting rid of extra nuclei and extra energy. Why does it happen? Because atoms hate being unstable. They want to be stable and happy. So our nucleus will drive out extra particles until it's back to stability. All right, let's chat about this bad boy. This is a graph that you guys will definitely be seeing on your test. So this is our belt of stability. If I zoom in on this, everything that you guys see that's kind of shaded, all those little dots, that's called our belt of stability. And these are just showing when atoms are happy versus when they're not. So if we look at our 2 different axes, right? On my x-axis, I have the number of protons. And on my y-axis, I have the number of neutrons. When we are at a 1-to-1 neutron to proton ratio, right? Let's go back to our PhET simulation really quickly. So let's go back here. Looking at the top left, I have 3 protons and 3 neutrons. That's a 1-to-1 ratio of proton to neutron. Lithium isn't shaking. It is happy in this state. So that's what 1-to-1 means. So going back to the belt of stability, when we have our 1-to-1 ratio, everybody's happy. But as our elements increase, as our number of protons increase, our number of neutrons also tend to increase. And when we have too many neutrons, we are no longer stable. So that's when they fall out of that belt of stability. And once they're out of the belt of stability, an element will do anything it needs to get back to a stable state, which means it will expel as many protons and as many neutrons as it needs to until it is stable and happy. This is a concept we will go over many, many times, and when I get back, I will go over the belt of stability with you some more. All right, so this is same, and this is exactly what I was saying. So if we look at the top right-hand corner of this, we have uranium-238. So uranium-238 is a naturally occurring isotope of uranium, but it is not stable. I'm going to zoom in. It is not stable. So the instability causes it to break down. And we're going to go over the different types of decay, but this little symbol up at the top is an alpha decay, which means uranium-238 will morph into thorium-234, right? That's also not super stable. So it will morph again and again and again and again and again and again and again until we get to the bottom left, where we end up with lead-206, which is finally stable. Again, it's not a big deal if you are super confused. That's what this whole set of notes is all about. Okay, so this is your next little thing that you're going to write in your notes. Letter A, under number 1, can a nucleus just shake off all the extra protons and neutrons in one go? For small atoms, the answer is yes, right? Think of a dog that goes into like a river and it comes out soaking wet and dripping in water, and they shake off all that extra water. That's what an unstable atom will do. It will shake off all of its extra protons and neutrons. However, the larger atoms, like I just showed you with the uranium, they have to decay several times. It's like a dog who would have to shake over and over and over again to get all the water off of them. Next, letter B, we're going to review isotopic notation. So we went over this, right? Unstable atoms go through radioactive decay, which we can predict and write out. Radioactive decay equations use isotopic notation, which is why we're reviewing it. So here's isotopic notation, right? We have our chemical symbol in the center, that's the big E. Up on the top left, we have our mass number, which is our protons and neutrons. And then on the bottom, we have our atomic number, which is our number of protons. Do me a favor, pause the video, write this. Write exactly what you're looking at with the E, the A, and the Z, and label everything in your notes. All right, welcome back. Going down to your next little section, I think I'm looking, okay, so see how this says A at the top left? This actually needs to be big letter D. Sorry about that. It reformatted when I copied it over. So big letter D, reactants versus products. This is a main concept of chemistry that we will be reviewing consistently this year. But I want to introduce it for you because this is something you will need for the equations that we are going to do together. So you'll notice on the left-hand side of these drawings, we have our reactants, right? A plus B in different colors. Our reactants undergo some sort of reaction and they become a product. Now our products are completely different, but you might notice on C we still have two yellow dots, right? And we have two yellow dots on the left side. We have one blue dot on the reactant and the product side. We have one red dot on the product and the reactant side. And we have one green dot on both sides. So my real life example for this is down below. When we look at the equation for photosynthesis, right? Even though we start with glucose and oxygen and end with CO2 and water, everything still has the same amount. There are 6 carbons on both sides. There are 12 hydrogens on both sides, right? Everything stays balanced. Moving down. Okay, so now we're going to talk about our types of radiation. So we were just discussing how that uranium particle went through all of those different phases, right? It went through all those different types of decay. This is what I was talking about, and we will have notes on this in just a second, so just hear me out for a minute. There are 3 types of radiation, or 3 types of decay, that we are going to chat about today. The first one is called alpha decay. Alpha decay is this first one on our little chart. Alpha decay is written as a helium atom because it is a helium atom, right? When a dog shakes off all the extra water, the water droplets are flying off, right? In our analogy with an actual atom, when an atom starts to shake and try to get rid of things, the easiest process for it to undergo is alpha decay, which is it gets rid of 2 protons and 2 neutrons. Well, 2 protons is a helium atom, so it is literally ditching a helium atom from inside of it, okay? We write that as a helium, just like here. Here's our symbol. I meant to activate my pen so I could draw on this, and then I forgot, like a real idiot, so pardon me for that. But we have a helium atom, that's how you write it, and then we write it in isotopic notation. So our mass of helium is 4, and our proton, our atomic mass number, is 2. All right, second type of decay is beta. So I'm going to read over here on the right. Beta particles, also called beta ray or beta radiation, is a high energy, high speed electron emitted by radioactive decay in the nucleus. So this is the second type of radiation we have, where we've shaken off our heliums, but now we need to shake off even more. So the inside of the nucleus can actually shake off this high-speed electron, and what this electron does is it actually gets rid of a proton. So you'll see that its charge is -1. It gets rid of a proton. 1 proton leaves the nucleus. And we write it as little e with a 0 because remember electrons have no mass, and a -1 charge because that is the charge of an electron. All right, and then lastly for you we have a gamma ray. All gamma rays is energy. So we talked in our last slides, right, about fission and fusion. Fission is the splitting of atoms, and it releases energy. That's what we agreed on. Well, radioactive decay is fission. The atom is being split apart, and it is emitting energy. So gamma rays is just the energy that's being emitted. I promise this will make sense soon. All right, going down, here is exactly what I just said out loud, but as your notes. So go ahead and please pause the video and write all of these. All right. So our radiation types, alpha and beta radiation, they are very, very low energy, right? Alpha radiation can be stopped with a piece of paper, like something super thin causes a barrier, right? Beta radiation can continue through a piece of paper but gets stopped by a piece of wood, versus gamma radiation, and I promise when I get back we'll talk about this more, gamma radiation to stop it would require like a 6-foot slab of concrete. And that's all we're going to say on that for right now. You don't need to write anything down. Okay, so this is the point in the video that I want to make sure that your notes look just like mine. So I'm going to click this, if it lets me. Of course, it's not going to let me. Stick with me for a second. I'm going to show you my notes so that you can see it. Radioactive decay. So your notes should look basically just like this. Reactants and products, I would love if you would write that, but you don't necessarily have to. All right, we've got our types of nuclear radiation. Make sure you write the examples in isotopic notation. And then last thing, please write out the chart that I have at the bottom of this, the chart that I was just going through with you, because that will be useful in a little bit. All right. Okay, now is the point that we are going to go to the pages that you guys glued in. So you should have the nucleus radioactivity sheet as your first sheet. Go ahead, first step here, pause me, write all of the symbols that I have on this slide in those boxes at the very top of your radioactivity paper. Now, I am going to take you through some examples. So, we have our 3 types of radiation here, right? We're going to start with alpha. We're going to go over an example of alpha decay. So we have our reactant, which is our uranium-238. That's on our left. Now we have the number 92 at the bottom. That means that uranium has 92 protons. And let's verify that. I've got that pulled up right here. Uranium should be number 92. And if I look down, it's all the way at the bottom. Uranium, number 92. So we just verified that. Okay, going back. So this arrow means that there's a reaction, or for us, some radioactive decay, which means that uranium-238 is not stable. It is not happy. So it needs to shake off some particles to become stable. So the first kind of decay that it will go through is alpha decay, right? Which is that helium that it gets rid of. It's going to shake off a helium. So what you'll notice here is that we have shaken off our helium, right? And then what we have, our product, is thorium-234. So you're probably like, okay, well, where did you get the thorium-234? Remember, when we have products and reactants, they have to be balanced on both sides. So let's look at all these top numbers in pink. I've got 238 on my left, which means I need 238 on the right. What is 4 plus 234? It's 238, exactly. And if we look at our bottom numbers, our number of protons, we had 92 protons originally with the uranium, which means after my reaction, I need 92 protons. Well, helium has 2 protons, and that got shaken off, which means my resulting atom has to have 90 protons. And if we go to our handy-dandy periodic table, let's look at number 90, thorium, okay? So all you guys are doing in this, you're doing a little bit of like super basic algebra, where both sides need to equal the same thing. Let's look at a beta radiation really quickly. We're going to start with our thorium-234, right? That is more stable than the uranium is, but it's still not happy. So it's going to go through another phase of decay, or like the dog, it's going to shake off more, right? So beta decay, we know that we're going to lose our electron. Our electron's on the far right-hand side. Electrons don't weigh anything. So we know that we're going to have 234 as our atomic weight for whatever our product is. And you see that under the Pa, right? Let's look at our charges really quickly, our protons. So thorium has 90 protons, right? If we undergo beta decay, we are losing a proton. So what minus 1 equals 90? Because I need 90 protons on both sides, 91. So 91 protons over here on the Pa minus 1 from the beta decay equals 90 on the thorium side. This is now balanced. See how the numbers on the top on both sides match the numbers on the bottom on both sides? That's what we're looking for. And then lastly, let's look at gamma ray decay. So I've got uranium-238 again, right? That's my reactant. Let's look at my products. I have a helium atom that got shoved off. So we lost 2 protons there. And I know that I have gamma ray production here. But gamma ray production has no mass and no charge. So it doesn't change anything. So when we look at this, all we're really looking at is if our numbers are going to line up. 238 on the left, so I need 238 on the right. 4 plus 234 equals 238. 2 protons plus 90 protons equals 92 protons. Everyone Gucci there? All right, let's go to our next slide if it lets me. Okay, so this is directly from your page of your first glue-in page. I'm going to now pause this video for a second because I need to put this on an app where I can draw out with my Apple Pencil. So this was the first video. There's another link on Canvas to video part 2. Please find that, click that, and we'll pick up from